Hello everyone. So today I'm excited to present our research about improving CNN generalization via Late-Epoch post-training weight averaging, which is our method. So this work is conducted at FPT University, addresses a very practical yet often overlooked challenge in deep learning pipelines, which is how we gonna select the final model checkpoint for deployment. So I'm gonna walk through on how we come up with this idea and our experiment setup and the result we have. So first of all, let's start with a standard practice that we all follow. So after training a CNN, we usually pick a single best checkpoint, which often based on the validation loss, but there is a hidden risk here. As you can see in the graph, the validation performance near convergence is rarely stable, so it fluctuates significantly due to the mini-batch sampling and the optimizer noise. So selecting a single point is essential a gamble that you might be picking a transient noise spike rather than a model that truly generalized. So why do we use post-training averaging? So you may ask them why we don't use the other methods like ensemble or stochastic weight averaging or model soup. Why ensemble are effective, but they are computationally expensive during the inference phase, which you have to combine the inference of many different models. And the model soup is aggregate across independently fine-tuned models. So you also need to multiple training and fine-tuning attempts to have those checkpoints. While the stochastic weight averaging is required to change your training schedule and cannot be applied retrospectively. It's used a cyclical and high contrast learning rate during the late epoch training to explore the parameter before averaging it, which is on a quite different purpose compared to our method. So, and our objective was to develop a post-training strategy, something that is cost-free and model agnostic and can be easily applied to any model that's already finished training. So our proposed solution is very simple, powerful. Instead of relying on one checkpoint, we aggregate model parameters from a selected window of the final number of n checkpoints. We compute the final model parameters as a simple element-wise arithmetic mean that crucially is a post-training operation. It's at zero inference overhead, and the final average model is still just one single weight set of weight. So you can see here's the full pipeline of our experiment. So we use two different leaf datasets, which is Burmese leaf dataset and tomato leaf disease dataset. We also apply the pre-processing data into the Burmese leaf dataset to denoise the background of the dataset. And after that, during the training phase, we use a queue to storage the last 10 checkpoints to use it for averaging for our method. We use 5 different CNN architecture. It's BGG16, ResNet 101, NetNet 121, MobileNet B2, and EfficientNet B0. So the result, the config we use is to ensure a fair comparison. We maintain an identical hyperparameter for both our baseline and averaging method. This means all accuracy gains we report are attributed solely to the averaging strategy, not to any change in optimization process. So the result we get after using our method on tomato leaf disease dataset, we can saw that the accuracy change ranging from the lowest is about 0.8% and the highest is 7.6%. We saw that the ResNet 101 and the MobileNet B2 saw the most dramatic improvement. On the Burmese green leaf disease dataset, the highest improvement is from EfficientNet B0 with 4.27, and the next is MobileNet B2 is about 3.42. And we also conducted a study on selecting the window size end. As you can see, the larger window generally led to more stable performance. While accuracy was stable for most values, we found that the n equal 10, it consistently provided a most robust result across different architectures, making it our recommended default choice. So near the convergence, the model entered the flat basing where multiple configurations have similar training loss but different generalization behavior. So by averaging this point, we move the final solution toward the center of this basing, reducing the sensitivity to the stochastic noise and resulting in a more reliable model. In conclusion, the Late-Epoch averaging is a simple, producible, and cost-free enhancement for CNN pipeline. However, I want to highlight a critical practical consideration is that its effectiveness is depend on the convergence. For example, if your training configuration is suboptimal and the model hasn't reached that stable low loss basing, the window might include the heterogeneous solution that could actually degrade the performance. So therefore, this window should be chosen to span only the final stable segment of training. And in the future, we might investigating in adaptive window size selection to automatically detect the stable convergence phase. And also we want to expanding the evaluation to a larger scale benchmark data set and maybe on other architectures like transformers. Thank you for your listening. If you have any question, I'm ready.
Okay, thank you very much for the presentation. Questions, comments?
Yeah, would you please go back to the parameter you compared it and yeah, here. Okay. So looks like n is equal 10 is your super parameter. Okay. So how do you know 11, 12? It's worse than 10.
our research, our research that the number of hyperparameter here I want to choose is it should be based on the early stopping that you set, because it's depend on the conversions, the range, the conversion range of the models. So if it's not in the conversion range, this checkpoint could make the model performance worse. So you have to set it below the amount that you set for early stopping.
Yeah. So because
So in this case, I was experienced on two data sets, and I both set it about 10 to 11 to 15 early stopping. So I set I recommend the number of window size is 10.
yeah, that's the most important. Particularly if you take a look at your DenseNet 121, it looks like if you keep increase your n number, then you can reach more.
No, there's another method that's used like it's averaging all the checkpoint from the beginning of training to the last epoch, but it's for each spot is have a different way for them. So it's some other method that I didn't mention here.
Wait, it's better to think, deep. How do you, when do you say, make it conclusion? You need to tell people why it's there, right? Thank you.
I have a question. My question is something relevant to that of Professor Wu. And I think the accuracy is one important criteria. But apart from accuracy, there's another criteria. It is robustness. So probably you need to make a compromise between accuracy and robustness. So it means if you use the window, okay, I am sure the noise will be removed, will reduce, but the sensitivity will be less important than with the increasing of the size of windows. You understand? Sensitivity will reduce. It means robustness is not sure it is working. Sensitivity, so it means if there's a change of the model, probably you have a fixed data set. You change the data set, and we get the same result, similar result, or if there's some quick change within the data set and the reaction of the model is the same or not.
I want to have a small talk with my team here. Sorry, can you repeat it again, please?
Okay. How is about the sensitivity change if you increase the size of the window? Sensitivity of the result. You follow me?
Can I clarify your question again? What you is asking that if I increase the model window size, does it in fact affect to the model robustness? So you have to look up your training curve, like it does not have a constant end. So you have to rely on your training dynamics. Like when you at the end of the training stage, when maybe like you have to check what end is suitable for your training dynamic, because it may be last 5 epochs is increase validation loss, so, and maybe like 15 epochs is increase validation loss. We don't know. We have to check and get the window size suitable for your data set and your suitable task. Yeah. But in this two data set we experiment, we see that n equal 10 is good for us. Yeah. I don't know that satisfy your question.
Anyway, thank you very much.